Hi, my name is TJ Rogers. I'm on the board of directors of Enovix, and we're doing a little experiment today to show the amazing energy capability of the Enovix battery. So I'm here in Denver with my brother who collects cars. So that's my brother. This is Lamborghini he's got here. And there's a Aston Martin James Bond car over there. And you can see it's a classic garage with all the signs and stuff like that. Main thing I'm here for is it's got a lift when he works on his cars, and I'm going to run that lift with an Enovix battery. I got with me Russ Fossler, who's an alumnus of Enovix. Ross is an expert in power engineering, and today we're going to do a demonstration that equates power, how much energy you put out over unit time, to mechanical energy. So we're going to talk about this tiny little thing here, which is just a shade over an eighth of an inch thick. This is an Enovix battery, one that would go in your cell phone. And then we're going to do a demonstration that involves the Enovix battery and the Lamborghini Gallardo here, which weighs 1,500 kilograms. I want to explain a couple things first, so you can get a calibration, a human level calibration for how this stuff works. So the first thing I'm going to do, I'm going to ask Ross to shine his flashlight from his cell phone into the camera. So right now, this is a standard cell phone. It's a standard flashlight. You've all got them. And he put it up close to the camera, and you get the light output of 1 watt. That's a 1 watt light emitting diode. And actually, the light energy in that beam is significantly lower than a watt because turning electricity into light is not that efficient. So all I did, I showed you a light, and I said the light was 1 watt. Now, watt is an electrical engineering term. It's a term of power, energy per unit time. And in electrical engineering terms, and the last time I'm going to talk about this, 1 watt is equal to 1 ampere times 1 volt. So that's double E. If I take this light and run it for 1 second, I have 1 second times 1 watt, same power we talked about, and that's equal to 1 watt second. And if you're a geek, and I'm a geek, a watt second is a unit of physics is called a joule. So that light that you saw burns 1 joule of energy per second. If I talk about 1,000 lights, and we easily have enough power here to turn on 1,000 of those things, and instead of turning it on for 1 second, I turn it on for 3,600 seconds. I picked that number because that's an hour. So if I run 1,000 lights for an hour, then that is equal to 3.6 million joules. Here you have 1,000 lights, so you're burning a kilowatt. So burning a kilowatt for 3,600 seconds is equal to 1 kilowatt times 1 hour. 1 kilowatt hour. So that you guys all know from your electricity bill. You pay, if you're in Idaho, you pay 16 cents for it. If you're in California, where we have inefficient utilities, you burn 32 cents. So 1,000 of them burning for an hour is 16 cents worth of power. And that's what we're talking about in what comes out of the grid. I'm trying to relate this amount of energy to mechanical energy. That's why we've got the car here. So here we've got one of the capacitors we're going to use to charge with the cell. And I just want to let you know how much energy is in this. We just charged this thing to 270 volts. So this is a typical industrial high capacity capacitor. This little circuit right here converts normal current into the high voltage that the battery takes with pretty good efficiency. So I'll just back away and let Russ show this demonstration.
So as TJ says, there's 270 volts in here. A lot of energy stored in this. We're going to demonstrate that energy.
The screwdriver was used to short the capacitor, which meant all the energy in it came out all at once. It's a steel screwdriver, and it appears that we've also made ourselves a welding machine here, where the screwdriver is now attached to the capacitor. Now, that's one capacitor, and that demonstrates the energy of it. To move a car, you have to have more energy than that. So here I've got 8 of them in a pack. And then I've got a second pack, and down below a third pack. So we have 24 of those capacitors that welded the screwdriver, and a power supply that turns battery current into the current and voltage the capacitors need to operate, which is the same as the power used to run the motor to lift the cart. So this is sitting on a lift here. And then we're going to compare that amount of energy to what's in the energy you hold in your hand every day, take for granted, and you shouldn't. Now I'm going to talk about mechanical energy. Energy is energy, and it can be thermal, heating, steam. It can be mechanical energy, lifting, gears, chains, or it can be electrical energy. So all I did was tell you earlier that a kilowatt hour will run 1,000 of those bright lights for an hour. The formula is simple. The energy required to move an object is mgh. Any high school student, physics students know that. This is the mass you're lifting. In that case, it's a car. This is the force of gravity, the gravitational constant. That's how hard gravity makes that car lift. So that'll be different on different planets. Here it's the standard. And then h is the height. So I'm going to do a calculation here. The car is 1,500 kilograms, so 3,300 pounds. So we're using metric because the equations are metric. So 1,500 kilograms times the gravitation constant beyond where we need to talk, but that's 9.8 meters per second squared. That tells you how much force is on that. That's mass times height, and we're going to talk about raising it to height of 1 meter. So think 3 feet. So this question says, how much energy does it take to lift a 3,300-pound car 3 feet in the air? And we've done that math beyond the scope of this thing. But if you use exactly that equation, you get 14,700 joules. And we told you what a joule was before. So that's mechanical energy. Then the idea, of course, is to use an electric circuit to raise it, measure the power or the energy out of in the electric circuit, and put the energy into the battery. In other words, use the battery to lift the car. The energy in the battery is back to the electrical version of energy. The energy in the battery is equal to the voltage of the battery times the total current that you get from the battery times the amount of time that the battery will put out that much energy and voltage. So in this particular battery, it's rated 26.5 watt hours. And the particular case of Enovix is they jam that much energy into that tiny thin little battery. Just an eighth of an inch thick, so it can fit in the cell phone, and the cell phone can still be thin. So this is straight calculation coming from the battery. The battery's got an average voltage of 3.6 volts, and it has specified a current times time, so you can do high or low current. But this is 7.35 ampere hours. And that multiplies out to 26.5 watt hours, and then you convert to joules like we did earlier. And there's your energy. So that's what it takes to lift a car 1 meter, and that's how much energy is in the battery by spec. That is, the battery will get replaced if it doesn't deliver that. This has got a 3,300-pound car and takes that much energy to raise it 1 meter. The energy in the battery is that means it can raise that car 4.7 meters high. So we haven't got time to go through all that today, but what we will do is show you the battery charging the capacitors, which form a power supply that runs the motor that runs the lift. Now we're going to charge the capacitors with the battery. That'll take a few minutes because of the maximum current that we can put in our battery chargers. So this is the battery charger that takes 3.6 volts input and outputs the triangle wave of power that charges these batteries eventually to the same voltage, about actually 300 volts, a little bit more than you saw. So I'll ask Ross to bring over the battery, hook it up to the conversion circuit that converts it into high voltage power, and we'll be ready to see if this thing will actually lift the car. Here we've got the battery. I got it taped down so it doesn't fall. We've got the two clips that take power from the battery into the voltage converter. You can see the light flashing. Basically, this is a thing that dumps charge, and every time the light flashes, it's taking some charge out of the battery and dumping it here. We've only been a few minutes, and these 24 capacitors are now already charged to 94 volts. And you can see 94, 95, this huge load, how fast the battery can charge that load. The conversion board says we're now at 299 volts. So we're charged. We'll just leave the battery hooked up to, leave the battery hooked up. It'll continue to charge it. So as we use power from the capacitors, the battery will recharge the capacitors. The output of the capacitors is a standard 20 ampere, 240 volt plug. So we're in effect connecting this through this to store energy as we have high draw into this directly into the car. Okay, Ross, let's do it. Okay, so here we have a standard lift, lightweight lift for a garage that lifts 5 tons. Electric motor, 2,200 watts. Uses hydraulic fluid and hydraulic pump. The piston is here, and the piston raises those yellow arms, and that raises the car. The thing is plugged into 240 volts, 240 volts, 20 amperes, which is in a conduit, so it's pretty heavy-duty wiring. So I've lifted the car up using the 220 volt, and I'm going to mark it. So we've lifted the car that far. Yank the plug. Doesn't lift anymore. Now we're going to plug the plug into, and pull that out a little bit so they can see it, into directly into the battery circuit. Okay, so now we're running off the Enovix battery. This is one battery charge of the set of capacitors worth of lift. So we've raised it 9 inches. So let's go see how it worked out. So the answer we got was 9 inches. The theoretical is 30, and the 30 comes from perfect efficiency, which it isn't, of a motor and a hydraulic system. So you saw the thing raise 3,300 pounds, 9 inches, and the efficiency is about 1/3. That is, our batteries charge the capacitor, and about 1/3 of the energy in the capacitors raised the car. 2/3 of the energy that the battery put into the capacitors was used for waste, made this room hotter. At least you saw a car moving upward by 9 inches from a battery, and we can do that 3 more times today before we have to recharge that battery. Okay, thank you.